That's what I was doing. I was sleeping all day. I worked all day long. You guys get a day off on Monday. I don't get a day off.
We should get off on Monday, and then you guys should get off on Tuesday.
We just had a day off last week. We had 2 days off last week. Okay. Like I said, we're going to start chapter 3. The first section, we're going to take a couple days. We're going to split it into 2 parts. Today, specifically looking at graphs of exponential functions, features, things like that. And then on Tuesday next week, we will get into applications of exponential functions, because there are a lot of them. A lot of real-world applications of exponential type functions. So, first off, let's start with a question. Is x squared an exponential function? What do you think?
Yeah.
Yes. Why? Why do you say yes? Because it's got an exponent. Seems logical. Agree? Anybody disagree? What is it? It's a straight line.
No, I'm just going to go like...
No, I don't lie. It's not a straight line.
Okay. It's going to look like a parabola, right? Here's the answer. Here's what I'm getting at. And this is just to see where we're at, because instincts right away are exactly what happened. It's got an exponent. It's exponential. It's not exponential. It's algebraic. It's a polynomial function. Linear, quadratic, cubic, all of those kind of things. Those are algebraic. Even rational functions that we just finished up. Those are all algebraic type of functions. Where x is down in the problem. It's the basis. Okay? An exponential function is one that has the variable in the exponent. Whenever there's a variable up in the exponent, that is an exponential function. Okay? And those, not that it matters all that much, but those are in the category of what are called transcendental functions. Okay? So the key part is recognizing that an exponential function is one that has a variable in the exponent. That's what makes it exponential. Those of you who are juniors in the class, when you get to the ACT later this next semester, step number 1, when you see problems like this, is to recognize that, oh, this is an exponential equation, and then start to work on how do I solve this, how do I work with this, which we'll talk about in this chapter. But the first thing is to recognize that it's exponential. Okay? Variable in the exponent. And the idea is when you take a look at the 2 to the x, the 2, if you remember back to last year, and again, it depends on which teacher you had in terms of how it was explained, but 2 is the multiplier, if you will, okay? 2 times 2 times 2 times 2 times x number of times. That's what the x is representing, okay? You're multiplying by 2 repeatedly is the idea, which is why it's growing. Something would be growing exponentially because you're doubling it over and over and over and over again, okay? So as we go into that, let's go quick check here. You don't have to write this down, just a quick check. 3 tables. One of them is linear, one of them is quadratic, and one's exponential. Let's start with the first one. What do you think?
Linear.
Why linear?
Because it goes up by the exact same amount.
Yep. If you think about a line has a constant slope between any 2 points. It grows at a constant rate. So as x is going up by 1, in this case, y is going down by 3. Down by 3, down by 3, down by 3. Therefore, that is linear. Okay? That is a linear function. How about the middle one? Okay, why is that one exponential? There's the multiplier. That's what makes something exponential, is that repeated multiplication. Times 3, times 3, times 3, times 3, times 3. This one is exponential. And therefore, the last one is the one that's quadratic. Hopefully, you can kind of see the y values like the symmetry of a parabola. 13 on one side, 13 on the other. 8 on one side, 8 on the other. 5 and 5. 0.04 happens to be the vertex in this case. So you can kind of see the symmetry of the parabolic part. Okay? But the reason I put this slide in here is because I wanted you to identify that exponential means repeated multiplication. That's what you're looking for. Okay? So, here's the basics. Let's start here. Basic equation. F of x or y equals a times b to the x. where A is your initial value. It's your starting amount, which also turns out that without any shifts or stretches or any of that kind of stuff, it's the y-intercept. And if you think about exponential growth, exponential decay, the reason why it's called the initial value is if something's going to grow exponentially, you have to start with something. That's A. It's what you're starting with. Okay? B, a couple things about B. And I'm going to put this in parentheses. B is the multiplier. B is your multiplier. Must be positive, but not equal to 1. And we'll talk about that in a second too. So on that last equation, y equals 2 to the x, 2 was the multiplier. Okay. First question, why can't B equal 1? Because then there's no growth or decay. If you're constantly multiplying by 1, nothing's changing. Okay? So that's again why I talk about B as being the multiplier, if you think about it from that perspective. Last part then is x in that equation, the variable, is any real number. That's your domain. You can plug anything you want in for x. Could be, you can raise something to a positive power, negatives, fractions, decimals, 0. You did a whole bunch of that last year in Algebra 2. Negative exponents and positive exponents and fractional exponents and all those kind of things. We'll bring those back as we need them. Okay? We're not necessarily going to spend a whole time focus all on that, but we'll bring them back when we need them. Okay? So, what we're going to use is we're going to use these two graphs as kind of our parent functions, if you will. So 2 to the x, 1/2 to the x, just to get a general idea of what's going on. And what do exponential graphs actually look like in general before we add in any of the shifts, any of the transformation type stuff like we did previously? Because that's coming on the next slide. So let's start here. Y equals 2 to the x. We already said that B has to be greater than 0. Because of that, that means we have a horizontal asymptote at y equals 0. Okay. What's the y-intercept? What is it? Somebody said it over here. 1. Y-intercept, remember, is that when x equals 0? What's 2 to the 0 power? Or anything to the 0 power. Again, we'll revisit that when we need to, okay? But for now, anything to the 0 power, if you remember, is 1. Okay? We'll revisit the y a little bit later on. But anything to the 0 power is 1, which means we've got a y-intercept right here at 0, 1. And if 2 is my multiplier, whatever I start with, we could give this a context if we wanted to, whatever we start with, is it going to grow or decrease? Yeah, because you're multiplying by 2, right? So it's constantly getting doubled, and you're getting bigger and bigger and bigger. Here's what the general graph will look like. There's your general exponential growth. Before we go to the next one, quick general question. What if I changed it to y equals 3 to the x? Yeah, it'll go a little bit steeper. It'll be a little bit, the idea is it's going to grow a little faster then, because now we're multiplying by 3 instead of by 2. Okay, so when you change that b value, the graph it still has the same basic shape, same horizontal asymptote, same y-intercept. It just will be a little bit steeper because it's going to grow a little bit faster. But one of the things I said to the other class, this is exactly what you would love to do. If you put money into an account, you'd love your money to do that. Grow exponentially, and all of a sudden, hey, look at how much money I have. This is great. Now, it doesn't happen that way, by the way, but it'd be nice if it did, okay? If you had that grow exponentially. I told you we're going to deal with applications next week on Tuesday as we move into the second part of this. Population is one. If you think about like bacteria growth. Bacteria grows really, really fast. Exponentially, okay? That's an example of population in general. Population of a city a lot of times grows exponentially. things along those lines. Then we get into one over here, okay, where if we go through, let's kind of compare. First thing, horizontal asymptote, still the same spot. That didn't change yet. What's the y-intercept on that graph? 1 again, for the same reason. 1/2 to the 0 power, still 1. Okay, so we still have that point. And now here's the question: when when my multiplier is 1/2, what's happening? Decreasing. There it is. Whoever said that, it's decreasing. Okay, because think about if you're multiplying something by 1/2. Well, now you've only got half as much. Then you've got half of that and half of that, and so it's actually getting smaller and smaller. So instead of exponential growth, you're going to have exponential decay. It's going to look something like that. You start off with something and it decays at a rapid rate. It decreases. Application in general, which again we'll talk about next week. If you think of either in chemistry or biology where they talk about half-lives, okay, that's basically what's going on. Is you can go carbon-14 dating and you can talk about half-lives of certain substances and all that kind of stuff. That's an exponential decay idea. Well, yeah. I mean, I couldn't go into depth on it, but there you go. You got it. All right. So there's your kind of your parent functions, if you will. Okay? So now we're going to add in the shifts and all those kind of things as like we did previously in the previous chapter. Okay? Now we're going to add in the h and the k and shift those graphs. Okay? So here's your general exponential function with shifts included. So notice it's the same general, a and b to the x, but now we've got the h and the k in there. Reminder, h is your horizontal shift, but in the opposite direction of what it looks like. Remember, anything horizontal is opposite of what you would think. K is your vertical shift. Take the whole graph and shift it up or down. And when you shift everything up or down, that means that horizontal asymptote is going to go with it. So instead of being at y equals 0, maybe it moves up 2 to y equals 2. Maybe it moves down 3 to y equals -3. But the horizontal asymptote goes with it. And because the asymptote goes with it, that means the range is going to also be affected as well, because you're shifting things. We'll look at that when we get into some of the examples. And then the final part, I put this down again. A again is your stretch or shrink. What I really want you to focus on though here is anytime you see a negative, remember, negatives deal with reflections on the graph. So if A is negative, then it's a reflection over the x-axis. It's a vertical reflection, okay, up and down. If the negative was in with the x, up in the exponent, then it would be a horizontal reflection, left and right, over the y-axis. Okay? So negatives are reflections. That's the biggest thing. And in one of the examples today, we'll take a look at that. So the process we're going to get into here in a second is we're going to look at the function as if it was this type of idea. A times b to the x. What's my starting function look like? And then we're going to take it and shift it. Okay, but we're going to start off with, all right, what's A, what's B? Let's focus on that and then do the shifts and stuff from there. Okay? Here's kind of a summary. So of all the things, and I put it in two different parts. So if b is greater than 1, that means we've got exponential growth. If b is between 0 and 1, the only difference here is you've got exponential decay. Here's kind of just a quick summary of what's going on. These are the things we're going to take a look at when we try to graph these. And you can just add this to your notes here. Domain we already talked about. All real numbers. You can plug anything in for x. It's always all real numbers when you're dealing with exponential functions. There is no restriction on your domain. Your range is most of the time going to be from whatever k is, your vertical shift, and above, from k to infinity. If there's a reflection, then it might be negative infinity. But it's usually wherever that horizontal asymptote and above. Okay. This is an increasing function because of the fact that b is bigger than 1. It's exponential growth. Your asymptote is located wherever the shift is. However much you shift it up or down, that the asymptote goes to that spot. And as always, a y-intercept is when x equals 0. You plug in 0 into the equation and see what you get for the corresponding y value, depending on what the equation is. And that's the graph that we're kind of shifting and we're working off of. Those are the different pieces that we're going to take a look at. So just like in the last chapter where we were identifying holes in the graph, vertical asymptotes, identifying all those parts and then putting the graph together, these are kind of the parts that we're identifying here. The good news is I've asked this year, the third class, I've asked the other 2 classes, and both of them think this is a lot easier than what we just did. Okay? At the end, I said, well, what do you think? Easier or harder than what we just did? And both classes were like, this is so much easier. So, good news is coming. Okay? Only difference, and you don't need to write all this stuff down, only difference that I wanted to point out, and the reason why I put them side by side. When we've got exponential decay, it's a decay function. The domain doesn't change, the range doesn't change, the asymptote doesn't change, the y-intercept doesn't change. The only thing that changes is its decay instead of growth. Okay? And that's, like I said, that's why I put these side by side, so you can see that everything else is still the same. All right, how we doing? You ready for some examples? Ready to actually start putting this to practice? There's all the background knowledge. There's all the information that we're going to use. So now let me give you example number 1. Here you go. Here's your first example. Here's your first exponential function that we want to sketch an accurate graph of. And when you get into the homework, what I want you to do, this is the stuff I want you to identify if they ask you, on any problems where they ask you to graph. Okay? If they're asking you to graph something, this is what I want you to identify and then graph. Okay? What we're going to focus on, like I told you before, we're going to focus on A and B. And then we'll add the transformations from there. Okay? But I want to focus on the beginning part first. And then we'll add to it. All right. First question, what's the value of A? 2. Which means, we said that's our initial value, that's our starting point, that's normally our y-intercept. I'm going to put that point on there. Don't necessarily put it on because we're going to move it. But I want you to understand what we're starting with. Okay? Remember, by the way, when we did like all the shifts and stretches and stuff before, there was one point that I wanted you to label every time. If it was a parabola, it was the vertex. If it was an absolute value, it was the vertex of the v. You know, those types of things. I always said there's one point I want you to label. That's the point that we're going to label. We're going to shift to that point, okay, to the new spot. What's the b value? 3, which tells me what about the graph? That's my multiplier, which means there is exponential growth. Okay, we're looking at exponential growth because they're multiplying by 3. Okay, it's getting bigger. So, again, don't graph this yet, but that tells me that in general, here's what it looks like. Here's the general shape of the graph that we're now going to move. Okay, that's why I said don't graph it yet because I'm going to erase it anyway. But this is, if I got rid of this plus 2 for a second, there's the graph of 2 times 3 to the x. Now we'll add in the shifts and stuff from there. Okay, now we'll make this, we'll move things around. What is the horizontal shift? 2 to the left, therefore I'm going to put negative 2. Okay? What's the k value? What's the vertical shift? Nothing. Which, right away, if I'm not shifting this up or down at all, where's my asymptote located? It's still at 0. Y equals 0. That didn't move. Okay? All right. So let me go back to the graph now. Let's add the shifts in here. We said the a value was at 2. But we're going to shift that 2 to the left. Okay? And we're not going up or down at all. So that point is now coming over here. Horizontal asymptote is still at y equals 0. So I can put that in. And we said based on our b value, our multiplier, I know that this is an exponential growth equation. So I can now kind of sketch in the exponential growth. Oops.
Good enough.
Yeah. Let me move that back. There we go. All right, so there's the general shape of the graph. Now, let's add in a few things. Y-intercept, remember we said was when x equals 0. So, plug it in. See what you get. Okay? All you're going to do is plug in 0 into the equation, just like you've done previously, and see what you end up with. So if I plug in 0, I get 2 in the exponent. Quick refresher, quick reminder. Be careful. This is a simple mistake you could make if you're not thinking. When you're evaluating order of operations, we do not do 2 times 3 first and then raise it to the exponent. Exponents come first in order of operations. Then we do the multiplication second. Okay? It's not. So in this case, I'd have 2 as a power. Well, 3 squared is 9 times the 2 gives you 18. My y-intercept is 18 in this case. Okay? Which is way up off the top of my graph up there. Okay? So remember, when you're finding that y-intercept, do the exponent stuff first, then the multiplying stuff second. Order of operations says that's the order. And now if we go through, let's finish this off. What's the domain of this graph? And all exponential graphs, all real numbers. So I'm going to put negative infinity to infinity. What's the range? From 0, not including 0, because there's an asymptote there. It's approaching 0, but not going to actually get there. You don't have to worry about cross points here on this one. Okay? So from 0 to infinity. And there's the range. There's what this graph would look like. Any questions before I move into the next example? Anything that we just did that's not quite making sense that I can clear up for you before we move on? Okay, then let's keep going. Here's example number 2. All right, same thing. I'm going to start with A and B, and then we'll add the shifts and stuff from there. What's the A value? What is it? 1. There is a 1 technically in front. 1 times 1/3. So there is a 1, which means normally, before we do any shifts, normally there's my y-intercept. There's the point that's going to get shifted right there. What's the B value? 1/3, which tells me what about the graph? This one's going to be decay. So right now, again, you should have in your head that there's my y-intercept, and I know that this is kind of a decay graph. Now we add the shifts. Okay, now we go through and start moving stuff around. Horizontal shift is where? Yep, we're going 1 to the left and 1 up. Okay, plus 1. So we're going to take everything and go left 1 and up 1. So that point is now right here. And that point just got shifted left 1 and up 1. Because we moved everything up 1, that's where the asymptote is located now. Because of that being shifted up 1, the asymptote goes up 1 with it. And we said in general, this is exponential decay, so we can kind of sketch that in. And there's at least a decent sketch. We will find one more point. We'll put the y-intercept down there again in a second. What's the domain of this graph, though? Let's do some of the easier stuff that you don't have to do any math to. Domain's always all real numbers. Yep. Negative infinity to infinity. Okay, how about the range? 1 to infinity. That graph is from 1 and above, not including 1. So make sure you have a parenthesis at 1. Okay? Not including that value. It doesn't ever actually quite get to 1. And finally, let's go back to the y-intercept, and then we'll add that point to the graph. If I plug in 0, what do I get for an answer? 1 1/3. If I plug 0 in, I get an exponent of 1. 1/3 to the first power is 1/3. Plus 1 gives you 1 1/3, or 4/3. Which is about right there. Okay, which now we've got a second point on our graph, that just to kind of confirm that we were doing things correctly. So first one was an exponential growth. Second one was a little bit of exponential decay. And now I've got one that's just a little bit different. There's a special part here on the next one. How we doing? Okay? So far, am I accurate in saying easier than rational functions? Okay? For the most part? All right. Take a look at this example. There's a specific reason for this example. And it's that negative that's up in the x. So what does that do to the graph? Again, let's start with A and B, and then we'll add the shifts and stuff from there. What's A? 1. So once again, y-intercept that's going to be shifted is starting right there. What's the B value? 3, which tells me we have exponential growth. Okay, so we know that part of it. Let's go to right away then. So you should have an idea kind of in your head what that graph looks like. Now let's start changing it. What's the horizontal shift? Was it? It's not 1. There isn't any.
Oh, I guess because it's
Yep.
addition.
You didn't. Yep. Because of the fact that it's addition, there's nothing added or subtracted to x in the exponent. Okay. There's nothing up here in the exponent that's being added or subtracted, so there is no horizontal shift. Vertical shift? 2. Okay. Which means there's where your asymptote is located. Y equals 2. So we're going to take this graph and we're going to move it up 2. So that point is now up at 3. Horizontal asymptote is at 2. And we said that this is exponential growth, so we'd have something looking like that. However, there's one thing I haven't accounted for yet. The negative. What does that negative do? Close. It is a reflection. But because it's attached to the x, it's a horizontal reflection. Meaning, if you can visualize, if you picked this thing up and completely flipped it around and then set it back down, that's what's happening. Is this part's getting reflected over here, this part's getting reflected over there. So therefore, what is this graph turning into? This is now decay because of that. And I'll give you another explanation as to why that makes sense in a second. There's the exponential growth graph reflected horizontally. Becomes exponential decay. Let's see what you remember back from Algebra 2. That's really just a negative exponent. How do you get rid of negative exponents? What is it? I just didn't hear it. See if you remember. What is a negative exponent? How do you get rid of that last year? What if I had like 3 to the negative first power? You have the right idea. It drops it to the denominator to get rid of the negative. So 3 to the negative first power is really 1 over 3 to the positive first power. So 1 over 3. A negative exponent turns something into a fraction, which is where the exponential decay is coming from. This is really, 3 to the negative x is really 1/3 to the x. That's really what's happening. That's why it's exponential. We'll go more in depth later on, but I wanted to see if we can at least refresh your memory here a little bit. Anytime you have a negative exponent, it turns it into a fraction. It drops it into the denominator, and therefore, in this case, we ended up with decay versus growth. Okay? Couple of these. Y-intercept's not too bad on this one because technically we already have it anyway. It's on the graph. But if you take 0 and I plug it in, 3 to the 0 power is 1. plus 2 more gives you 3. And like I said, it's already on the graph. So it just confirms that that is the y-intercept. Domain? All real numbers. Okay, same thing again. Negative infinity to infinity. And range of this graph? 2 to infinity. Yep. How we doing? Okay? Not too bad? One last minor concept that we got to take a look at before we end this one. Yeah, Aiden?
So is that a horizontal or a vertical reflection?
That's a horizontal reflection because of the fact that before it was that growth and we reflected it left and right. Also because the negative is attached to the x. That's why it's horizontal. Yeah.
So if A is negative, then it's
Correct. Yep. What you really need to think about is if the negative is attached to x, it's horizontal. If it's not attached to x, then it's vertical. Okay? Where if it was vertical, this then would flip over that and it would change to a whole different graph then. Okay? All right, here's the last thing we need to talk about. We've talked about growth, we've talked about decay, we've talked about all this kind of stuff. Well, there's this nice number that they call E that just keeps coming up over and over and over again in specifically engineering and financial type of applications. Okay? That, in math, E is a number. Okay? It's kind of like pi, if I'm going to try to explain it. And what I mean by that is, pi kept coming up over and over and over again, so finally they said, we need to call this something. Let's, rather than write out 3.14159, all that kind of stuff, and just keep writing it all out. It was something that kept coming back over and over and over again, so they called it pi. E is the same thing. This is a number that just keeps coming up in future applications and things that just kept coming over and over and over again. And finally they said, let's call it something. Let's call it E. Reason they called it E? The guy who discovered this, his name was Leonard Euler. Last name is spelled E-U-L-E-R. He called it E after himself. Okay, after his last name. Okay. So, yeah. So there's this number that's approximately 2.71828, and then I believe it repeats from there. 282828, it keeps going from there. Okay? And so, if we take a look, let's say I wanted to graph this. The point I want to make is it doesn't change much. It's just a different base. It's just a different multiplier. Where would the horizontal asymptote be? Y equals 0. There's no vertical or horizontal shifts here. What's the y-intercept? 1. If you plugged in 0, even though it's base E, raised to the 0 power still equals 1. That doesn't change. So we still have the 0.01. And is this exponential growth or decay? Growth. It's bigger than 1. So it's growing. It just happens to be growing by a specific number. So it actually looks just like, this is just a special type of exponential growth. That's all this is. And because I know you're super into this and wondering where this comes from. No, I know you are. You can't fake it. El, you just look disgusted, El. Here's where it actually comes from. Not that you really need to know this, to be honest. Not that you don't have to write this down. But here's what this actually is. If you were to type this into your graphing calculator, it turns out that this looks just like one of the rational functions we've been dealing with that has a horizontal asymptote at E. If you were to graph this graph, as it goes to the end behavior we've talked about, it approaches E as it goes to positive infinity, and it approaches E as it goes to negative infinity. This will come back later on when we start talking about some financial applications. But just as a heads up, that's what's going on. This is where E is actually coming from. Okay? Which, last example then. Let's do one with E. Let's wrap this up. And again, the main point I really want to make is that there's not much difference. What's the A value? 1. What's the B value? E. Which means, normally, there's your y-intercept before we do any shifts or anything. And E tells me that it's exponential growth. So in my head, I already know kind of what the graph looks like. And let's now move it. Horizontal, where are we going? 1. 1 to the right. Vertical, down 2, which means the asymptote is at y equals negative 2. So let's take that point and the asymptote and let's move it. 1 to the right and down 2. There's your new point, new asymptote after the shifts. And again, we said E is basically an exponential growth function. So we can go through and we can sketch that in. I'm going to skip the Y-intercept for a second. We'll end on that. That's actually one of the reasons why I put this problem in here. We'll plug in 0 in a second. We'll find the Y coordinate. What's the domain of that graph? All real numbers. Just because we changed the base doesn't mean that I changed anything that I could plug in for x. So negative infinity to positive infinity. How about the range? From negative 2 to infinity. Okay. So again, most of this is pretty much exactly what you were doing. Okay? Just with E versus 2 or 3 or 5 or whatever it is. Here's one of the reasons why I did this, though. If you have your graphing calculator, go ahead and take it out. I want you to locate the E button on your calculator so you know, like right now, if I were to plug in 0, it's not real easy to do in your head. So I want you to know how to use the calculator, where your points are located. By the way, somebody had asked in, I don't know if it's this class or previously, about the idea of storing different values for x in physics. Don't worry about that. That doesn't have any effect in here. It's fine. Okay? So if you've got x's stored to like 2 or 5 or 10 or whatever, don't worry about it. It's fine. It won't have an effect on what we're doing. So here's what, if we were going to actually type in and find the actual x-intercept here, or the y-intercept, excuse me, we need to take E and raise it to a power. Well, if you look right next to the number 4, there's the ln button. But right above that in blue, it says e to the x. That's the E. So if you hit second and ln, that should pop up. E to some power. And now you can type in. In this case, if you were to plug in 0 into that equation, you get negative 1 as an exponent. So I'm going to type in negative 1. Quick reminder, quick heads up. Once you're done with the exponent, make sure you arrow to the right to get out of the exponent. Okay? Because that minus 2 that's in the problem is not in the exponent, it's after. So I'm going to arrow to the right, and now put the minus 2 at the end. You hit enter, and you should get approximately negative 1.63-ish. Okay? Negative 1.63. Okay? So now, and like I said, that's the main reason I wanted you to find I wanted you to locate that E button on the calculator. So therefore, approximately negative 1.63. Well, if we take a look, here's approximately negative 1.63. Again, which happens to be on the graph, or pretty close to the graph that we already sketched. Okay. How we doing? Feeling okay? Doable? Hopefully? All right. We're going back to book assignments here for a little bit. I know you guys love book assignments. So, section 3.1, problem 17 to 41 odd. It seems like a lot of problems. They're not all graphing problems. Some of them are just saying, what are the shifts? Just explain them. Okay? Some of them are just typing stuff into the calculator, just practicing like what we just did. Type in e to whatever power. On any of the graphing ones, make sure that you show the work like what we just did. What's the A value? What's the B value? That kind of stuff. That's what I want to see. I want to see the parts that then lead to the graph. Okay? Otherwise, that's all I've got for you today.